Well, hey, good morning, Mr. Park.
Good morning.
Wow, look at this contraption.
So,
Is that a candle?
that's a candle.
Oh. And
This is a metal ramp.
okay.
And this is an Erlenmeyer flask, and there's a liquid inside.
Oh, it's water.
Maybe. Or
Oh,
maybe
it's
not.
clear, it's colorless, it looks like water.
So, anytime we have a liquid, the liquid will tend to evaporate to some degree. If this was water, and if I swirl this around, we would get water vapor inside the flask.
What's water vapor?
Water vapor is water in the gas form.
Oh, okay. Like humidity.
Yeah, evaporated water, right?
Okay.
Except, this is most likely not water. So I'm gonna swirl this around, and while I swirl it, I'm building up vapors inside the flask. Now they're invisible, you can't see them, but they're there. And so what I'm gonna do is I'm gonna open the flask, and I'm just gonna tilt the flask, and all of the liquid that's in the flask is gonna stay in the flask, but I'm just gonna tilt the flask so the vapors can escape, and we'll see what happens.
I still see the liquid. The liquid's not pouring down the ramp.
No, I don't want it to.
Whoa, whoa! Are you okay?
I'm okay.
Whoa.
I'm okay. Let's try that
So
again.
what's down here? Is there like gasoline down here or something?
No, this is a liquid called hexane, and hexane is a molecule that is just like octane, and octane is what you know as gasoline.
Huh.
So
Oh, I know gasoline evaporates really fast.
it does, and everything in its family does as well. So let's pour the vapors again. Again, no liquid is leaving.
Whoa! Oh, that's cool. I still don't understand why it's burning that way. Like the flame comes from the bottom of the ramp and goes up.
So
Wouldn't it start from the flask?
because I'm not pouring any liquid, because I'm just pouring the gas is more dense than air.
Oh, okay.
The gas made from the hexane. So that's why it falls, and as it falls, it's able to go down the ramp. Once the gas reaches the flame, that's when the reaction occurs and it ignites. And it travels back up because I poured a stream of gas, and then it ignites and works its way back up.
Oh, I wonder if I zoom in really quick, if we do it one more time, if I kind of get the camera right down on the ramp, if I can see some vapor maybe pouring out.
Okay.
No guarantees.
It might look like wavy lines, kind of like the...
Like a mirage of like heat above the street.
That's right.
Whoa!
Did you catch that?
I don't know. Maybe the kids can watch it in high definition, but
Okay.
wow, that's very cool, Mr. Park. Thanks a lot.
All right.
Hey there, Mr. Trow here, Mr. Park behind the camera. What we have here is we have a glass jar that is filled with a clear colorless liquid. I'll let you know this liquid is water. Okay, it's very exciting. We also have a few different drinks here. Okay, we have the Pepsi family.
Chug.
No, these are old. We've got the Pepsi, full strength Pepsi, and we've got Diet Pepsi. 150 calories in this one, and this one must be healthy for you because it has 0 calories.
Is there a half-strength Pepsi?
I don't know, is there?
You said full-strength Pepsi.
Oh, sorry. So what we're going to do here is we're going to take a look at how these behave in the water, okay? So I'm going to take first Diet Pepsi, okay? I'm going to pop it in the water. And it is floating, even if I push it down. Yeah, it floats. So you could probably determine that whatever the overall density of this pop can is less than the density of the water. Okay, now regular Pepsi has a lot more in it, a lot more sugars, sodium. Okay, so I'm going to pop this in. And you can see it slowly goes down to the bottom, which means that full strength Pepsi, not half strength Pepsi, full strength Pepsi must be more dense than water. Now we thought it'd be kind of interesting. You saw how fast this dropped. Maybe we take a look at Coke and see if Coke's any different. Okay, I personally am a Coke fan. I don't know about you, Mr. Park.
Me too.
Yeah, Pepsi, ugh. Diet Pepsi goes flat right away. Can't stand it. Here's some Diet Coke. We got a floater. Okay, and full strength. Coca-Cola Classic. Oh, that plummeted.
That went down pretty fast.
That went down real fast. That's interesting. Let's see if there's a comparison here between the two. Nope, they have the same number of sugar. Well, actually, Coke has slightly less sugar in it.
Maybe the
But
syrups.
it has a little more sodium. Okay, I'm gonna try one more thing. I'm gonna try a little bit of magic. Okay, I'm gonna take that Pepsi. We all know that the Pepsi sank, right? I'm gonna take the Pepsi, and I'm going to make it
What
float.
happened?
It's floating. It's magic. I don't expect you guys to understand how it works. We as teachers, we've developed our sixth uncanny sense of different types of magic.
Can I touch it?
You can, yeah, go ahead. No, don't. Okay, be careful. You broke the spell.
I just restored reality.
Yeah. Maybe at home you guys can think about what I did differently in that trial that made this possibly float. Think about the density of everything around, the water, the atmosphere, okay, the shape of the can. Maybe you can figure out why the magic worked until Mr. Park screwed everything up. See ya. See that, Mr. Park?
What is that?
It's my friend, Cartesia. Been with me a long time. Cartesia and I have a connection. I can actually communicate with this test tube Cartesia inside this bottle. Yeah, he's a friend of mine. I can tell him to dance if I want him to. I just have to think really hard. And I can make him move around.
Amazing.
Dude, you broke my concentration.
Sorry.
When I say don't talk, I mean don't talk. Okay, connection's made. So once the connection's made, we're together. I can make him do whatever I want. I want him to rise up. I don't have to look at it. He can rise up. Doesn't matter. I want him to go down. He goes down. Okay, you can do whatever I tell him to do. Okay, so now here's the cool thing. Mr. Park and I have been teaching together for a long time. And we don't really have to communicate either. We can communicate telepathically. So I'm going to transfer my control over Cartesia to Mr. Park. And all he has to do now is just move his fingers. And he can control it. That's amazing. What do you want it to do? You want it to go up or stay down?
I like it. Well, I guess I gotta go up eventually, right? Let's bring it up.
Oh my God. And back to me. Thanks, guy. That was nice.
I don't understand, Mr. Trow. Are you going to explain how you did that?
Sure. Well, this is actually not really a friend of mine. It's just a test tube. So if you look inside the test tube, it's filled with water up to a certain point, but there is a pocket of air. And so we all know that air is less dense than water. So air wants to float, kind of like, if you're in the pool and, well, you get the picture, okay? But here's the cool thing. Right now, the density of that air is small enough that it has enough lift, kind of like a hot air balloon.
Like buoyancy.
Yeah, enough lift to hold up the weight of the test tube. But what I'm doing, the secret I'm doing, is I'm pushing my thumb into the back of this 2-liter bottle. And if I do that really quickly, watch what happens to the air. Do you see how when I push the 2-liter bottle, the water cannot compress. It's a liquid. It doesn't compress virtually none at all, okay? So what it does is it forces the liquid up into the test tube and compresses the air. So we learned in class, density is mass over volume. If we make the volume smaller, if we make the denominator of a fraction smaller, the overall density of that air then is going to be larger. And so if we get this set perfectly, just a little bit of compression of that air drops the density, makes the density larger, and the buoyancy now is lost, and the test tube falls. But you could do this at home very easily. It's magic.
Cool.
Bye, Cartesia. Hey, stop playing with my toy.